белый. Да, можно начинать.
Okay, our next speaker is Sergey Lando, and the title of his talk is Skew, characteristic polynomial of graphs and embedded graphs.
Thanks, and I must admit that it is a rather strange feeling to speak at a conference for jubilars whom I remember both as high school students when I was the same high school teacher. But it's in fact a great pleasure, and I'm very grateful to the organizers for inviting me to this conference. It's one of the very first ones where we are able to give talks and listen to each other and to communicate in person after long months of distance communications. And I'm going to talk about a very simple topic, which is called the Skew characteristic polynomial of graphs and embedded graphs. The talk is based on my joint work with my former master student, Ria Dogra. And the choice of the topic is due to the fact that several years ago, we started to discuss this subject with Lyonya. It originates in the willing to establish a connection between two domains which seem to be rather similar in several features, but up to now there is no visible connection, and the domains are cluster algebras on one side I've forgotten whether there is U or A. U, it's okay. Sorry. And on the other side, we have Vassiliev's theory of finite type not invariants. Finite type not and link invariants. Invariants and the objects that arise in the two topics are look similar but not identical. Here we have quivers, which are oriented graphs. And also embedded, usually oriented graphs. And on Vassiliev's side, we have just graphs that are not oriented, and also embedded graphs. And there are some equivalences which are called mutations on the left, and Vassiliev's four-term relations on the right. Now, the Skew characteristic polynomial is probably one of the first examples of a possible internal relationship between these two parts. And before defining it, let me recall an obvious definitions of what are characteristic polynomials. If you just have a matrix, then its characteristic polynomial is the determinant of U times identity matrix minus A. And in particular, this allows one to define the characteristic polynomial of a graph. Let me take a very simple graph for this purpose. And if we number somehow the vertices of this graph, then we may associate to it its adjacency matrix. Matrix consisting of zeros and ones, A of G, which is which has 1 on the intersection of the ith row and j's column, if and only if the vertices I and j are connected by an edge. And to this matrix, we are able to associate a characteristic polynomial, which I will denote Qj of u. It is just Q Aj of u. If instead of a graph we take an oriented graph, let me orient the graph somehow, then I'm able to associate to this graph its adjacency matrix. Which now will be skew symmetric instead of being symmetric. It has zeros on the diagonal, and that will be -1, 0, 1, -1, 1, 0. So we put in the matrix entry either 1 or -1, depending on the orientation of the edge, and we also can consider the characteristic polynomial of the oriented graph, which is just the characteristic polynomial of this skew symmetric matrix. Now, let me say that a graph is G is non-degenerate provided its adjacency matrix is non-degenerate over the field of two elements. Over the field of two elements, and I introduced the graph invariant called nondegeneracy. In spite of its simplicity, it's rather important. It is one provided G is non-degenerate. and 0 otherwise. Let me underline that this 1 and 0 are not just the determinant of the adjacency matrix of a graph, because I consider them as complex numbers rather than elements of the field, of the two-element field. And now I'm able to define the skew characteristic polynomial of a graph. Sorry. I'm slightly puzzled because it was a different. Okay, let me use just another letter. P J of U of a graph G in the following way. Pj of U is equal to the sum from k equal to 0 up to the number of vertices in G, pk of G times U to the power V of G minus K, where V of G is the set of vertices of G. And pk of G is the sum U of G restricted to U, where U is a subset of V of G, consists let me take a chord diagram D, which is nothing but a circle, to be more precise, an oriented circle, with several chords in this, with several chords. Chord diagrams are considered modular orientation preserving diffeomorphisms of the circle. So this is just a combinatorial object rather than a continuous one. And to each chord diagram, one can associate its intersection graph. G of D. in the following way. We just number the chords in some way, and the vertices of the graph are the chords of the diagram, and two vertices are connected by an edge if and only if the corresponding chords intersect one another. So the intersection graph of this chord diagram is the very same graph I have already used in my previous illustrations. And I wish to say that this graph can be oriented in a number of natural ways. What are the ways to orient this graph? Let me add an additional piece of structure, namely a cut point. If I cut my diagram, the circle of the diagram at some point that is not the end of any chord, then I can untie the circle, making it into the line, and the chords will become arcs. So what we obtain is the arc diagram. Arc diagram A of D, which of course depends, the arc diagram depends on where we cut the circle, and the arcs preserve, preserve the numbering from the chords. To this arc diagram, one can associate its intersection graph exactly in the same way. But this intersection graph can be already naturally oriented, depending on oriented. The orientation will be chosen like that. We orient each edge according to the order of the left ends of the corresponding arcs. Since the left end of arc number 3 precedes the left end of arc number 2 in the orientation of the line, we orient the edge 3, 2 from 3 to 2. The same for the left ends of the arcs 2 and 1. The left end of the arc number 2 precedes the left end of the arc number 1. And now, a not complicated theorem states that the skew characteristic polynomial of the graph G of the graph G of D of the intersection graph of the chord diagram coincides with the skew with the characteristic polynomial of the oriented graph A of D. G of A of D. This is G of A of D. An immediate corollary asserts that the characteristic polynomial U of G of A of D is independent on the choice of the cut point. Of the cut point and the graph realization. What does the last statement mean? One and the same graph can be obtained as an intersection graph of several different chord diagrams. And generically speaking, it's not true for arbitrary graph, but for some graph it is true that the graph can be obtained as the intersection graph of several different diagrams. We take such a chord diagram, we choose a cut point in this chord diagram, and we obtain an orientation of the edges of this graph, but computing the characteristic polynomial of the resulting antisymmetric matrix, of the resulting skew symmetric matrix, provides one and the same result independently on which orientation has been chosen. So for a given intersection graph, there is a set of distinguished orientations, none of which provides, all of which provide one and the same characteristic polynomial of the corresponding skew symmetric adjacency matrix. And what's specifically interesting in this theorem is that the left-hand side depends only on the graph. We can compute it knowing about the graph only, not having no additional information about possible orientations. In particular, there are two graphs, for example, with 6 vertices that are not intersection graphs. All the other graphs are intersection graphs. All the other graphs with 6 vertices are intersection graphs, but there are two graphs which are not intersection graphs, which are 5-wheel and 3-prism. And we are able to, using the definition, we are able to compute the skew characteristic polynomials, which are and here we have the 9 alpha plus 12 u squared. Like that. And it happens that neither of these two graphs admits an orientation of the edges such that the characteristic polynomial of the corresponding skew symmetric matrix coincides with this answer. So in spite of the fact that a huge family of graphs admits such orientations and many such different orientations, this is not true for these graphs. No orientation leads to now let me explain what does this invariant to do, what has this invariant to do with Vassiliev theory of finite type invariants of knots, and how it can be extended to embedded graphs so that we associate to it an invariant of links. In Vassiliev's theory, he defines a knot invariant of finite orders, and to a knot invariant of order at most 10, he associates a function on chord diagrams with n chords. N chords. This function, he proved also that this function satisfies so-called four-term relations. And such functions are called weight systems. Since I'm not going to go in Vassiliev theory in detail, let me just formulate the statement. Let it be a statement that the Skew characteristic polynomial satisfies four-term relations and is therefore a weight system. Hence it defines some knot invariant. This is due to the obvious fact, those who know what four-term relations are and what is the relationship, for example, with Jacobi relations in Lie algebra, will easily verify this fact simply because the non-degeneracy of the adjacency graph of the adjacency matrix of the intersection graph satisfies these four-term relations, and they easily follow. And what is a way to extend the Skew characteristic polynomial to embedded graphs? In order to do that, I need first to extend the notion of non-degeneracy. Of embedded graphs. Many people have already told what are embedded graphs here, and in particular, Maxim Kazaryan has done that a few minutes ago, so I will not recall that. And if gamma is an embedded graph, then I'll define its non-degeneracy being to 1 or 0, depending on whether it has a single phase and 0 otherwise. If gamma, why this definition is consistent with that one? If you take a chord diagram, then we are able to associate to it an embedded graph with a single vertex. With a single vertex. We just make the circle into a vertex and each chord into a ribbon. And it happens that this embedded graph has a single edge, has a single face, if and only if the intersection graph of our chord diagram is non-degenerate. Has a single face. If this is a diagram D, if and only if GOD is non-degenerate. Therefore, it's very natural to extend the notion of non-degeneracy to arbitrary embedded graphs, not with a single vertex, but not with just a single vertex, but with arbitrarily many vertices in this way. If the graph has a single face, if the graph has a single face, if its boundary is connected, then it is non-degenerate. Otherwise, it is degenerate. So we know how to extend non-degeneracy to embedded graphs. And now we would like to know how to extend the polynomial itself, which is in fact easy. We just to extend the skew characteristic polynomial we need to compute this pk, this coefficients pk of gamma, which is just the sum of non-degeneracies, sorry, of the induced subgraphs, where now U runs over all subsets of the set of edges, all subsets of the set of edges of the graph, of the embedded graph gamma, such that this subset consists of k edges. And then we will have a definition. We will have a natural definition. Now my time is more or less over. Maybe there are a few minutes left. Let me mention two other important properties of the skew characteristic polynomial, which related first to, let me formulate it as a theorem. The skew characteristic polynomial P G of U takes constant values on primitive elements. In the Hopf algebra of graphs. Let me add here delta-matroids. Which stand for embedded graphs. I do have no time to explain what is the Hopf algebra structure on graphs and what are primitive elements in this Hopf algebra. And up to change of variables, for intersection graphs of chord diagrams, for intersection graphs of chord diagrams, the skew characteristic polynomial coincides with the GL1 superalgebra weight system. Once again, I do not have enough time to explain what are weight system associated to Lie algebras or Lie superalgebras. Let me stop here.
Thank you. Questions? Can we treat your results as an attempt to classify cluster algebras?
No.
No?
Definitely no. This is an attempt to find invariants of quivers that behave nicely with respect to mutations. That's the direction is like that. Of course, if there will be some definite progress, then this could help to classify.
So, but do you expect that these invariants or these characteristic polynomials may allow you to know something about maybe center of these algebras or something like that? No?
It's too far from from now. I cannot assert that there is no connection at all, but up to now, these are very first steps.
Okay. Thank you very much. Let us thank speaker again.